Okay, so this is lab 5. I'm in Sakai, and let me get down to lab. Lab is right over here, RLAB05.R. I've already downloaded that, and I've also downloaded a file called credit.csv. So if I go to my desktop, I've got a folder called lab05, and it has credit.csv in there, and I'll use that for the entire lab. And then I also got lab05 in open in WordPad. So let's get started. The first thing that I have to do is to go to lab05 folder, and you can create any folder of your choice and give it a right click to the file and copy the path of the file. So that's a path of the file. I'll use that to set the working directory path. So let's open the RStudio, and I'll do the same thing we have done a million times. Set wd and the path, change the directions of the slashes, and we're good to go. Okay, so I can even do list.files, and I can see there is one file, credit.csv. So the first thing that we have to do is to read this file into a variable, into a data frame. So let's call that data frame to be credit, read.csv, and then credit.csv, that's the name of our file. It has been read. We can look at the structure of this. Structure is all fine, nothing unexpected. It's very similar to what we have done in the past. With this file, there are 1,000 rows in there. And one thing to be noted is that 17th column is default. That's our target variable. Throughout the lab, our focus is to predict whether this person going to default or not. That's the purpose of our model. So this is a 17th column default that we are targeting. Everything else is a predictor. Okay, and similarly in the lab, I have one syntax for summary, so you can do summary as well and do credit. And this is a summary, and we can see everything looks great. There's some unknowns, but that is all fine. Duration, something that we have already seen previously. So there is no point in investing more time into that. Let's go to the next step, and this is where I start cutting the samples. So before I cut the random sample, one for training and one for test, let me set the random seed. And as I mentioned many times in the class as well, the whole purpose of setting the seed is that if I run this algorithm, the script multiple times, I do not want to pull different random samples because they'll give me different outputs and I'll be kind of confused. So if I'm doing any kind of troubleshooting, I won't be able to get the same random sample. So that's the purpose of setting the seed in this way. Every time I run this, I'll get the same sample. Okay, and hereafter, I'll create a random set of numbers between 1 to 1000, and there'll be 900 of those because I need 90% of my data for my training sample. However, if you look at this particular expression, it is a little bit different from our previous versions of sampling. In the previous version, our sample was something like this, 1000 and then 900, and what that means is 900. What that means is out of 1000 numbers, give me 900 random numbers. However, many a times we do not know how many rows would be there in our data set. So in this case, it's okay. We just got 1,000 rows and we put 1,000 in there. What if they are like 4,228,000? What will you do in that case? First, find out how many rows are there, and then based on that, do some kind of slices of the data. Instead of that, what we can do is we can use a function called nRow, which gives you the number of rows in a data frame. So my first expression over here is n rows of credit. So how many rows are there in the credit? We'll put that number over here. So we know there are 1,000 rows. So it will put 1,000 over here. And then I use that n row credit, which is 1,000 multiplied by 0.9, which is nothing but 90% sample of those 1,000. So I'll have 900 number over here. So once I hit enter, the strain sample will have 900 numbers, random numbers in the range of 1 to 1,000. So just let's see what is there in there. So sample, and we got 900 numbers in the range of 1 to 1,000. So far so good. Now with that, what we have to do is something that we have already done in the previous class. We have to create a random training data set. So the name of the training data set going to be credit underscore train, and we'll include all those rows which are in train underscore sample, which are 900 rows randomly chosen between 1 to 1000, and all the columns. And we'll hit enter. And similarly, we can do the same thing for test. So this will remain the same, train. We just have to reverse the sign over here, minus. And then over here, I'll make it test. And this will have all the rows which are not in train underscore sample. So if we want to see, okay, and row of credit underscore train, we're gonna see 900 rows in there. If I do the same thing with the test, I'm gonna see 100 rows in there, in total 1000. And these are totally different rows, you know, there's no overlap. We do not want any overlap. Okay, so that is all fine. We have taken care of this step as well. So now we have to run a naive Bayesian classifier, and for this Bayesian classifier, we have to install a package called E1071. So let's install that package E1071. I'll go to the internet, we'll find out the package, and we'll download it. Okay, so it's downloading, and now it's all installed. Let's call the library of E1071. So now the library has been called, and now all the functions which are there in E1071, they're available to us for usage. Okay, and with that, we have to run this particular function. All it does is it calls a function called naive Bayes, which is calling naive Bayesian classifier. It will give all the things which are predictors, which excludes the 17th column because 17th column is a default. And then what you're trying to predict, the target variable, which is default. And you hit enter, and the model has been created. The name of the model is credit underscore classifier. So naive Bayesian classifier runs on those 1000 rows with 16 predictors. Minus 17 means default is out, target is default, and the model has been created. Now let's do the prediction just like what we did with decision tree. The syntax remains the same. Predict the name of the model. Here it is credit underscore classifier. And what is your test data frame? So the test data frame is credit underscore test that we created right over here. So once we do that, all our predictions are stored in credit underscore test underscore predict. Okay, so now let's see credit underscore test underscore predict, what is in there. And we'll see a bunch of yeses and nos. And that is all fine. We can create some contingency table out of this. But we're talking about naive Bayesian classifiers. Many times we're interested in probabilities. Okay, so before we proceed to the probabilities, let's do something that we have already done a million times. Let's call GM models. I'll install that package GM models. The reason why I cannot find is because double quotes are not there. So I'll modify the scripts accordingly. So install.package GM model, and it will install that package in a couple of seconds. Okay, so package is installed. Let's call the library gmodels. And now library is installed. Now everything is available for usage. And then do the same thing we have done a million times. Do call the crosstab function. And all we are saying is that this is the prediction. This is a target column. And we do not want chi-square statistics. We do not need the table row properties. All we're and the name of the columns or dimensions is going to be predict and actual. So here is predicted, and here are the actuals, and we can see in total it's about 24% accurate, and this is on test. So far so good. Okay, so now comes the idea of how we can improve the performance of our naive Bayesian classifier. One thing that I talked about in the class was Laplacian smoothing, where we can add some factor to the counts when naive Bayesian classifier is counting those numbers or subsets for probability. We put 1 in there, so in case there is one calculation of the class where it comes out to be 0, it doesn't make everything 0. So that's what Laplace is equal to 1 is doing. It will put 1 into the count. Here it will not make much of a difference because we have such a tiny data sets, and the probability of anything missing with 0 probability is pretty slim. But when you're dealing with say text mining data sets, Laplacian smoothing is almost must. It's required. Otherwise, you're going to have zero probability. Okay, so we have done that, and let's do the same prediction. Okay, so here again we are running the prediction. So here are the new model name was credit classified 2, and this has Laplace is equal to 1. The previous one, which was credit underscore classified, didn't have the Laplace. And then we run the prediction on this particular model with the same data frame. And now all our predictions are stored in this. So let's do the cross tabulation of this and see how well our model is doing. So do a cross tab, and 59, not much of a difference. And that was expected because it's such a tiny data set. The situations where Laplacian smoothing brings benefit, that situation is not in here. Okay, so, but I just wanted to show you, how you can use Laplacian smoothing. All you have to do is to create one more parameter called Laplace and give some value to it, 1, 2, 3, 4, 5, whatever. Okay, so that is all done. One thing that I want to show you was that right now, if you look at credit underscore test underscore predict 2, you see yeses and nos, and that brings some information, but I'm actually interested in probability. So is it possible for me to have a probability of yeses and nos? And the answer is yes, you can do that. And it's very simple. All you have to do is to put one more parameter called type and put it to be raw. So if you do that, now if you look at credit underscore test underscore prob, you will have the probabilities of 100 test cases that we have in our test data set or data frame. So there's a probability of no and there's a probability of yes. And so this is what is coming out of prediction model. We can combine this with the actual information that we have, and we can see, okay, here was the actual yes, and this is what our model said. It said no. Is that very clear cut no, or is it like borderline no? And based on that, we can do some improvements in the model. So how to do that? So for that, I'll create a data frame called credit underscore results, which will combine those two information. So here what I'm doing is I'm calling data frame as a function. It will create 4 columns, 1, 2, 3, 4. The first one will be the actual value of the target variable, which is default, whether it defaulted yes or no. So that is the actual value. Then the second one is the predicted value. So the predicted value going to come from our credit underscore test underscore predict, which is which at this point in time is all the yeses and nos. So that would be that. And then I've got probability of yes and the probability of no from something that I've just created. So over here, so no and yes. So those are in the new predictor that I've created, or predictor data type that I've created. So these two would be yeses and nos probabilities. This would be yes and no in words, and this will be the actual value, whether the person really predicted or not. So let's hit enter and let's see how this looks like. So let's do head of credit underscore results. And we see 4 columns, 1, 2, 3, 4. So the first one is no, and this is also no, and the probability is like 2% of yes and 97% of no. So that was a good classification. Here we got mismatch. The actual is no, we say yes, and it's overwhelming yes. It's 94.6% yes and 5.3% no. So that is a big difference, and it's clear cut. Our model is not somewhere in the mix, in the gray area. It's clear cut saying that no, it's yes, when actually it's no. Okay, so we know that there's some scope for improvement for our model. Now we can, with that data frame, we can do a bunch of things. We can do subsets, and subset requires a data frame that you want to subset, and thereafter a logical condition based on which the subset will be created. So here logical condition is give me those rows out of data frame credit underscore results where the probability of yes is greater than 40% and probability of yes is less than 60%. That is to say, give me all those rows where the probability of yes and yes ranges between 40 to 60%. That's the gray area. So let's do that. And there are like, 5 rows, yes, yes, and 55, 44. So still it's working, but still it's in gray area. It's not that clear-cut demarcation between yes and no's. And we can actually see how many rows are there with that kind of problem. So 14 rows are there which are between 40% to 60% probability of yeses. Okay, so and another example I have is like to see all those rows um, where our prediction is wrong. So all we have to do is to again call subset function, subset this particular data frame called credit underscore result. Give me all those rows where the actual type, whether yes or no, is not equal to the predicted type. So this exclamation sign means not, and then equal means of course equal. So not equal to predicted type, and I hit enter and I get these uh, 6 rows in there. I can also do n rows and it will give me 24. 24, and that matches with the cross tab that we did previously. So it was 15 plus 9, 24. So this is the way by which you can do subsets of your test data set. You can further dig out, where your algorithm is going wrong, um, how many data points are sitting in that gray zone, which is like 49-51 split. It's a split, but still it's not that great a split. Okay, so that is all done. Let's install another package called Carrot. And Carrot is a great package for data mining and for machine learning. It has tons of tools in there, great visualization, great methods for cross-validation, boosting, bootstrapping, all this kind of stuff. So it's really helpful. So let's get into this package. And I've already installed the package. Let's call the library Carrot. And so library Carrot is called. So it's loading some packages. Okay, now everything is done. Okay, now here I will call a function called confusion matrix, which is nothing but something that we have already done previously, but this is a way you can create that cross tab without G models. Okay, so here I'm calling a function called confusion matrix, which is part of Carrot. It will take the predict type, what you have predicted, yes and no, based on our model. What was the actual type? So what was really yes or no? And then the positive, which I classify as positive, is actually the yes. So here we got yes and no, and we can say, okay, yes is positive. Many times if you're working, say, medical sciences, it could be category 1, 2, 3. You have to say, okay, category 1 is positive or category 2 is positive. So that's where it becomes handy. And we'd hit enter, and if you do CF, you get all kind of statistics about the confusion matrix that we previously had. We didn't have that much of clarity, but here we got a lot of statistics about our confusion matrix. So one thing is there, of course, the numbers do not change, 15, 9. So that is 24%. Here, no is 58. Yes is 18. So that is all great. 76% accuracy, which is not a surprise. 100 minus 24. We are off in 24 rows. So that is the reason 76% accuracy is over here. Kappa is a statistics that I'm interested in too. So I talked about kappa in the class, and it is 43.1% or 0.43. So far so good. And I also put some example how you can just call a specific statistics out of confusion matrix function. So you can do CF dollar overall, and then out of overall you can just call kappa column, and so it will just give you kappa. Similarly, you can do the same thing with the overall, accuracy, and you can just call accuracy. So this way you can go after each piece of information which is there in confusion matrix. Now, there are a bunch of people who send me an email saying that confusion matrix function is not working. They're getting an error. The confusion matrix is not found. It could be, it's highly likely it's because you did not install a package called Carrot. Or if you install the package called Carrot, you did not call the library Carrot. You have to do these 2 steps before confusion matrix becomes available to you.